Hey, welcome to Physics 2211 Lab 2. This lab we're going to be discussing some more of Newton's laws as they relate to drag. So the purpose of this lab, sorry, I got my timer here. The purpose of this lab is to demonstrate the effect of the drag force on the overall net force of the system by comparing experimental data against models with and without drag modeled. We'll get to that, like what that means more later, but essentially, you have a paper ball, drag affects it, how does drag affect it, and what are the implications of that for the modeling of it. The physics principles we're going to use in this lab: Newton's second law, F equals ma, or the derivative of momentum. Newton's third law, where every action has an equal and opposite reaction. The kinematic equation, and the velocity update formula. The results of this lab show that a paper ball falls slower in real life than just a model that does not take into account any drag force. This shows that the force of drag slows the ball down somewhat, and so a more accurate model takes into account drag, which is the second model we're going to make. So procedure for this lab, first we drop a paper ball from rest, we videotape that, we analyze that motion using tracker. Once we do that, after we do that, we're going to create a computational model of the ball falling. One of those we're going to include a model of the ball falling with drag, and one of them is going to be without drag, and one of them is going to be with drag. And then we're going to compare the results of those models to the real data. No drag model versus real data, and then drag model versus real data. So our initial conditions of the lab, the origin, obviously time is going to be equal to 0. The force of gravity is going to be negative 9.8 meters per second squared, because that's just the universal, that's the constant. Our drag equation is negative b, which is the drag coefficient, times the velocity squared, times v hat. The initial position is the origin. The system is the ball, and the surroundings are the air, floor, the person dropping the ball, really anything that's out, really anything not the ball in the room. Okay, and now for our data. So for our experimental data here, we can kind of see, I don't know if you can see my mouse in this, but you can see we have, this is like the moment right before 2 seconds is when the ball is dropped by the person holding it, and you can see it very quickly begins to accelerate, and then you can see the line kind of flattens out, showing the velocity is more of a constant here. That's going to be a little hint towards our drag. That's going to be a little hint towards the terminal velocity we're going to talk about a little bit later in this lab. So here's our glow script model for a no drag model. As you can see, it's perfectly parabolic, and the acceleration and its velocity is increasing. So acceleration is always more than 0. The absolute value of the acceleration is always more than 0 for the duration of the time period. Here we can see we just have b set equal to 0, and we don't update any drag force in the code here. Other than that, it's pretty simple. Now we come over here, we got position over time with drag included. So we're going to see how we have b set to a value here that we kind of got to by looking at the experimental data and kind of working backwards from there. Here you can see we got 2 lines here in our while loop. We got force of drag equals the vector of negative b times the magnitude of the ball times the velocity squared times negative 1, which is just the hat vector, and that's your drag equation. And then we update, and then we fnet is that plus the vector of just the the acceleration, or mass times acceleration. So some of the observations we're going to make from this. So as you can see, in our no drag model, we have a parabolic curve here where the velocity is always increasing, whereas in the drag force, that curve stops increasing at a certain point when the force of drag is equal to the force of gravity, and the net force equals 0, and there's no more acceleration. And we can also see that here in our experimental data. In real life, we also see a flattening out of the velocity of the acceleration, and we get a terminal velocity. So there's possible sources of error, bad drop. We added a force to it when we dropped it. Tracker error that could always have broken, and the video angle could affect. The perspective could make the data skewed a little bit. But other than that, what does it mean? So terminal velocity. So we're discussing terminal velocity here. So terminal velocity is when the net force of gravity and drag are balanced, meaning that F net equals 0, and thus we have no acceleration. We can identify this graph from the point the position versus time graph, where the velocity is aligned with a constant slope. So here in the glow script with drag, not here because there's no drag, so there's no terminal velocity. And here we can also see a terminal velocity. And what if the ball was thrown downwards? So if the ball was thrown downwards, we would actually still hit terminal. It would still experience terminal velocity, and the speed would actually decrease until it got back to terminal velocity, as you can see by this glow script model here, velocity versus time going back to 0. Okay, that's it. Thank you for watching my video.